continue with binder characterization, superfave test. And if you need a little background about superfave, I'll be glad to give that. I don't know about the familiarity of the audience with superfave test, but please ask. Like, I don't want to repeat something you already know, right? I don't want to assume anything. Also, and I want to, if something adds value, I love to provide that.
But there are 4 questions from the.
Oh, nice. Let's do that.
Sanya Rani.
Okay, let's do it. That's it. So let's go back. I got a few questions. I would love to answer those. Okay. 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 I'm going to answer all your questions. What is the current design method that US use? Astro 93 or Astro N3? So just to let you know, the states have the ability to use any design methodology they prefer to use. So in the US, there is no centralized system. So Cal, like I heard IIT PAVE or something there, right? Huh?
IRC is the main head.
IRC I know. And then there's a PAVE,
IIT PAVE software.
So the IIT PAVE software. Therefore, California has Cal PAVE ME. California thinks it's its own country, so they like to do the things their way. So every state has their own test. Astro 93 is an approved test method. New Jersey DOT does both ways, does Astro 93 and Pavement ME, both. So they do both of them together, they compare the results, and they are slowly, their goal is to completely transition to this new one. So at this time, they are doing both. Oklahoma does only Astro 93. I know that. So different states are at different stages of adoption of Astro 93. So that is. I hope that answers your first question. So US doesn't have any standardized method of that. Next question. I hope that answers the first one. Next one. Analysis tool was developed for ME design. Might have inbuilt methodology to perform a damage analysis.
What is given in that case, if a particular tool we wanted to use the ME design analysis, they need to give the input corresponding to their locality. Why do they further need to calibrate the result? I was not clear about the requirement of calibration here in the Astro ME design. In ME Astro 93, I can understand there's need for calibration specific to each location.
Yeah, 100%. So if without calibration, this model is pretty inaccurate. Okay. So let me just explain to you very clearly. This project was developed by Dr. Bigzak, the late Dr. Bigzak in Arizona State University. Okay. There were 700 test sections used over the entire US to calibrate the model. Okay. And its majority were in the state for obvious reasons. It's very familiar. Now, there were maybe, I'll just give an example, 5 sections from New Jersey to calibrate the model. Okay. So if New Jersey uses this model, it's going to be pretty inaccurate. There were only 4 to 5 sections used to calibrate the model. Okay. So if New Jersey DOT is using this model for very low volume roads, they are fine. The risk is very low. Okay. But if they want to use for heavy traffic, they have to calibrate the model for the specific state. Otherwise, it's going to be very inaccurate. So your answer is correct. You have to calibrate for each state and even different parts of the state, right? You can be mountainous region, you can be beach region, right? All of them have different climate requirements, different soil requirements also. So the soil is different, natural soil is different, mountainous region, climate is different, all of this is different. So different state, New Jersey is a small state, so one calibration is enough. But other states will need multiple calibration. So you have to calibrate the model for different states. So that will hopefully answer your question. Second question, that there is a need to calibrate for heavy volume, high risk locations, right? Otherwise, if you don't want to invest the money, then fine, you will have to take the risk. I hope that answers the second question. Okay, next one. In ME design, we are considering the elastic model. Correct. All right, so I'm going to explain dynamic modulus in the next section and as well. So that is correct. It is done um, two things. You mentioned about elastic modulus over 15 days. That is correct. You have to use elastic modulus for 15 days, correct? And I'm going to explain to you from dynamic modulus, how do we get to elastic modulus? I will explain that to you. The main question you asked was, uh, the impact of that I'll explain to you. There's another question that was asked in the same number 3. Just going up a little bit. Oh yes, reliability. If you are calibrating the model, you need to calibrate the model at 50% reliability. If you are using the model, you can use at 90% reliability, 95% reliability, whatever you want to use. Calibration should be done at 50% reliability without any factor safety. What's going on? Good. Okay, next one. Does that answer your number 3? I will talk to you about, I will explain the dynamic modulus. Astro ME is not an official guideline that is in practice. All right, couple of things. Astro ME is no longer, nobody has the mandate or power to require payment ME or Astro ME to be used by states. Nobody has the power. Every state does their own thing. So Astro 93 is a standard. Astro ME will not become a standard at this time because I just explained to you there is a significant amount of cost associated with transitioning to Astro ME. You have to do a lot of testing and many state agencies are refusing. Okay, let me give a simple example. When Astro ME came out, the first thing the politicians asked, will that lead to cost savings? I don't care how good this program is, right? The politicians and the upper administration ask, will that make my section thinner, right? So if you are constructing the same section 4 inches, but my actual payment ME will give me 2 inches, that means I'm going to save 2 inches of payment. That's all the upper administration cares about. So if the upper administration is not convinced that this is going to save them money, they will say, I don't care how good this program is. That is your problem. It is not saving me money. I'm not going to go there. That's a political decision. So every state agency has their own politics to deal with. So I don't think it will become a national standard, but it will be continuously be improvised, but it will be at the local level. So I hope I answered that question as well. In continuation with my earlier from where.
Sure.
Yeah. So in continuation with my previous question, this is an excellent question as well. You want to, if it's you want to take the existing payment. If it is for the subgrade, it doesn't matter wheel path or no wheel path. It is so low down below, so it doesn't matter. So you can take anywhere you want to take as long as it's under the payment section. Okay, so you can take that. You want to take as many samples as possible. The more samples you take, the more accurate is going to be your level 1 input parameter. If you do not want to invest, then you can use soil classification as I explained before. So does that answer your question? So you have to do, you asked in service. I would suggest if you're doing in service payment, you do falling weight deflectometer, and I explained yesterday how to analyze the data. There are softwares that will analyze the data and that will give you E1, E2, E3 of in situ payments. I hope that answers all your questions. I have one question pending. How does dynamic compress modulus relate to elastic modulus, which I will answer today. Did I answer all your questions? Everybody? You see? All right, sounds good. All right, I'm going to go ahead and keep going through the binder characterization. Okay, so right here, um, you have the asphalt is viscous versus elastic, and then you have an elastic solid right here, and then you have a viscous fluid right there. Okay, and critical. So that is what you're looking. You're dealing with asphalt characterization, and A and BTS correlates viscosity with pen. Will they go to hear me without that? Okay, without viscosity and penetration. Okay, and then it is dependent on temperature, rate of loading, and aging. Okay, so as temperature increases, viscosity drops. As rate of loading increases, the viscosity or stiffness increases, and aging the binder viscosity and temperature relationship. How to convert binder stiffness data at heat temperature using equation 2.0. Right here, ABTS. There is a simple viscosity equation, temperature stability. Right here, dynamic modulus. I'm going to explain this in detail. All right, dynamic modulus is a very important test. I want everybody's attention here if you can. This is done for hot mix asphalt. Can everybody see the board? Well, HMA, right? And you do this at different temperatures. Temperatures are given here, and I'll follow the same temperature, right? This year, so what you do is there's a sample, this is asphalt concrete. So it is asphalt in there, I don't need any confinement, right? It is not going to fall apart. And you apply vertical load, there is no confinement at all. Okay? And what you do is you apply load at a certain frequency, continuous load with frequency or time, right? And then you have servicing. Okay. All right. Now, you will get, so everybody understand that it's going up and down, right? And you're applying that load. And then you have spring, okay, with frequency. I think you can put some time. So it's legible time. Okay, so I'm over a certain amount of time, right? And then there is going to be strain, and there is going to be some lag, and then it's going to go like this, right? Same will follow the same. Everybody with me so far? So what you will see is the dynamic modulus is given by at any point sigma this versus this, right? So E star is given by sigma over epsilon, right? Stress over. That's your dynamic modulus. What happens is you run this at different frequencies. So this can be run very fast, all the way to 25 hertz, and as slow as 0.1 hertz. Different frequencies, right? And it can be run at different temperatures: 12 Fahrenheit, 40 Fahrenheit, 70 Fahrenheit, 100 Fahrenheit, 135. Okay. Now, this, of course, is very clear. This is for heavy traffic, fast-moving traffic. This is for standing traffic. 10 seconds, give or take, right? 0.1 hertz is 10 seconds. Right? So you have to do this test at every temperature at different frequencies. Everybody understood that? So there's a software, you put it in the machine and you will do that. Okay? Now, when you do this test, right? I'm going to erase this, okay, because I need it. Right here, what is going to happen? Right here, I'm going to plot with hertz frequency. Okay. And you're doing 0.1 hertz, right? To 25 hertz, correct? I just said that. And then you have E star line. So if I do this data set, right, and at very high temperatures, very low temperatures, asphalt is going to be very stiff because our binder is viscous. So, but as the frequency goes up, it becomes stiffer and stiffer. Okay, at lower frequency it flows. So it will be at high temperatures, it's going to look like this. Yeah. 0.1 Hertz. This is by time, but I can reverse it in a bit. Okay. So let's say this is done at temperature is I just say the same number, well F for some, right? And then there'll be another data set here, another data set here, another data set here, so on and so forth. It is going looking exactly reverse of that. There is no confusion here. This is in frequency, this is in time. One over the other, right? So if I change that and make that into, swap it, this is 1 over 25 and this is 1 over 10, correct? In time seconds, correct? So nothing, 0.1, sorry. That will be 10, correct, thank you. So time in seconds and the same thing will be reversed, right? And now I am seeing a drop in numbers, right? I'm sorry, I'm just off on that scale here. Right? So 1 over 10, right? 0.1. Thank you. Thank you. 1 over 0.1, right? And so right here, this will show exactly reverse. Correct? Everybody with me so far? Same temperatures. This is 12 Fahrenheit. And all the way, I'm not going to plot all of them, 130 Fahrenheit. Can everybody see that? Everybody with me so far? Okay. This is a project one, a level 1 requirement. You have to do dynamic modulus of hot mix asphalt. Okay. Now I'm going to explain this very important concept called time temperature superposition, what that means. Let's say that this is my, I'll pick this temperature, I like the 70 Fahrenheit, let's say. Okay. Okay. 70 Fahrenheit is my standard temperature, baseline, let's say, reference temperature. This is the beauty of asphalt concrete. If I just move this entire curve, I want everybody's attention, to the left, because it is colder than 70 Fahrenheit, right? And move this to the right, because it is hotter than 70 Fahrenheit. Move this to the right, because it is hotter than 70 Fahrenheit. Correct? Does that make sense to you? Horizontal movement, no vertical movement, completely horizontal. What you will see that it is true, all of them will directly follow a very smooth curve. That's what you see there. And I'm going to explain the significance of this. It's a very powerful tool. So I tested from different temperatures. This is my raw data. Everybody understand this? This is my raw data. But my shifted data is not raw data. I've analyzed the data, right? Now I'm going to draw this here. Okay. So right here, right, I have data measured only between these 2 points, correct? Everybody with me so far? I've only measured between these 2 points 1 over 25 Hertz and 1 over 0.1 Hertz, correct? That's the only real data. But I shifted this left and right and I got this data set right here. Everybody with me so far? This is what temperature?
70.
Only 70 Fahrenheit now. Only one real data set exists between these 2 points. That is the real measured data. Yes. Now look at the beauty of this. If did I test anything, this is 10 seconds, correct? I did not test slower than 10 seconds. Everybody with me so far? But if I extrapolate this, this could be as high as 1,000 seconds. Everybody with me so far? If I did not go faster than 25 hertz, right? But if I went all the way, then this could be as much faster than 1,000 hertz. Extrapolated data. Look at the beauty of this. To test the material at 1,000 hertz is pushing the limits of the equipment. Very expensive to do. Alright? But I could be very smart by just measuring the material at 12 Fahrenheit. I can get the data of 70 Fahrenheit at 1,000 hertz. Or 70 Fahrenheit at 1,000 seconds. That means I don't have to wait 1,000 seconds. Remember, I can shift anywhere. I just took 70 Fahrenheit. I could have done this entire master curve at 12 Fahrenheit. I could have done this entire master curve at 130 Fahrenheit. Can everybody see the difference here? So I have the ability to take any temperature, any frequency, just by doing a range of temperatures at a short interval. This phenomena is called time temperature superposition. I'm going to explain to you in a much more simpler fashion. Let's say what this means is this. I hope I can do a better job at this. If I take this material, 70 Fahrenheit material, I want you to physically understand what this means, and I load it for 1,000 seconds, it is going to deform a lot. It's almost equivalent to heating up to 130 Fahrenheit. Same impact. As if I'm heating the sample, or if I stood on asphalt here for 1,000 seconds, is as if I'm lighting a fire under the asphalt. That's what it means. On the other end, if I test the same thing 1,000 hertz, it's equivalent to me doing what? Doing what? If I test for 2,000 seconds, it's equivalent to me heating more than 70 Fahrenheit. What does this mean?
Very less temperature.
Yeah, cooling it. It's almost equal to cooling it. But look at the beauty of this, right? If I can also reverse the logic if I don't have a freezer, if I don't have a cooling methodology. So I can even go backwards and do inverse. Like, okay, I don't have a freezer in my facility to put 12 Fahrenheit. What will I do instead? What will I do instead? Test at the father. It's completely interchangeable. So we do this all the time. If a student comes, oh, Dr. Mehta, I need data at minus 50 Fahrenheit. Oh, I don't have a chamber for minus 50 Fahrenheit. What do? Test it at a faster range. You got it? So you can be very strategic. It's like, so in asphalt, you can get the data. And this is scientific. This is not empirical. This is material property. This is called time temperature superposition. And that is very powerful. To measure at any temperature and any frequency, I can get this. Is everybody with me so far? That's called the master curve. Okay? So you can see this number, 10 raised to minus 7 loading time. Can you imagine how fast that is? 1 over 10 raised to what? 10 crores? 1 crore, right? 1 crore is 7 zeros, right? Right? 7 zeros. Right, okay. So like that fast, who does that fast? Impossible, right? Not possible. That machine has to be very powerful to test that. All you did is you tested at 12 Fahrenheit and you got the data extrapolated. Look at it. 10 raised to 5 whatever seconds. That's a lot of time. That's 10,000 seconds. But now, without testing it, I got the modulus because I tested at 130 Fahrenheit. You got it? Everybody with me so far? Did I have any questions online about this? This is I want to explain something else about cutting. Okay. About this. Yes, I'll answer that question now about this. Everybody got that? Dynamic modulus. Okay. Now, There was a question online about what do I do with this information? Okay, I'm going to explain it. Again, I come back to the 15-day period. There's a question. How can I take dynamic modulus? 15-day period, I'll come back again. Okay? I have a daily distribution of those 15 days. Correct? I have axle load distribution and I have speed of traffic. I have temperature from weather data. Yes? Let's say now, today, right? What is the time? 11:15. Temperature is 70 Fahrenheit. A truck is coming at 10 hertz. What can I do? This is in the database of the MEPDG. The moment it sees this, it goes into this 70 Fahrenheit, 10 hertz, it picks this number. That's my E value, E1. Got it? So there's a question asked, what is the difference between elastic modulus and dynamic modulus? This I can now use for any temperature. In the winter, it becomes 12 Fahrenheit. It will pick 12 Fahrenheit. That frequency, the temperature in winter becomes 12 Fahrenheit, 1 hertz, tipping traffic, it can pick that number right there. See the beauty of that? So it picks the elastic modulus from the dynamics to any frequency, any temperature, appropriate number. That is to answer the question online. How can dynamic modulus be translated to elastic modulus? That's an excellent question. That's what it is. Does that make sense? Everybody understood that? All right. Level 1 and 2, use penetration, A and BTS. Viscos, you guys seen this machine? Viscometer? Yeah, it represents shear strength of asphalt, address binder strength and resistance to shearing. This is the DSR. I know we have a DSR here. I just saw the machine. You get the fixed plate going back and forth. And then you get G star, and you get the time lag G star sine delta or PG grade. You guys measuring PG grade right here? PG grade. Right here, level 1. This is a nice way to look at it. Level 1 is the highest level, right? Asphalt concrete, you can use superbay binder test. Different temperatures, 40, 55, 70, 100. And then you have different delta phase angle. Phase angle is elasticity. If the phase angle is 0, then it's completely elastic. Phase angle of 90 is completely plastic. And of course, asphalt is closer to 90 than it's not elastic. Right? Asphalt concrete is more elastic than asphalt binder. Why? Asphalt concrete, hot mix asphalt is more elastic. If I got the phase angle of hot mix asphalt, it will be around 45, 50 phase angle. Why? Yes. What is an asphalt concrete? Aggregates, right? And what is aggregate? Aggregate is more elastic. Binder is only 5%. Aggregates is 95%. So you have 95% of elastic material, 5% of this. Of course, the hot mix asphalt is going to be more elastic than the asphalt.
The aggregate combining with the binder is elastic, right?
Is more elastic than the binder. Right? That's what you asked. That's what it is. Yeah. Then you can just superbay binder grading PG 76 minus 22. You can pick that and then you can get the A, B, T, S. Now you can use superbay binder grade. You can use other information. Then you can do RTFO, rolling thin film oven, to look at aging. So you can get the binder properties in the LV design guide using short-term aging. Are aware of this? You put hot air at 85 Fahrenheit for 165 minutes. Yeah, correct. And it will age. It simulates aging during construction. It simulates aging during construction. That's why the word short-term aging, short-term overaging. Asphalt mix characterization, that's your dynamic modulus right there, right here. Reference temperature 70, you can pick your own reference temperature. Binder content is by volume, not by weight. By volume, binder content is twice that weight. So you are used to 5%, 5.5%, but by volume it becomes exactly double. So by volume it occupies twice the volume. And then you have the thermal conductivity. Why not? This is the number, raw data. 5 temperatures, 4 frequencies, 10, 40, 70, 100, 130 Fahrenheit. Look at the numbers. This is what the input data is from the testing. That's all you have to give, and it automatically calculates the master curve. It automatically picks the right beta during the analysis. Does that make sense to you? Automatically. All you need is this right here. If you're not going to do the testing, you can do level 3. You have to put the gradation, number retain 3/4 inch sieve, 3/8 inch sieve, number 4 sieve, and then passing number 200 sieve. Dynamic modulus is level 1, indirect 3, and that's your gyratory compactor. You guys see the gyratory compactor? So you have a gyratory compactor right here. We have that as well at the Global University. And then right here is the sample of 6. You're putting this out, and then you have to cut it into the right sample right there. The ratio is 2:1. So if the diameter is 4, the height has to be 8, and so on and so forth to ensure you have proper, don't have edge effects. Right here, 100 to 104, 147, or 1.5. I apologize. Oh, by diameter, right? So I'm good there. Standard deviation 1, parallel, and then the patternness, they look at that. Yeah, so remember, it's pushing that. Cost of test is between $50,000 to $150,000. That's the machine. That's the whole machine of doing the. That's the test. I just explained. You have to do a sinusoidal test, and then you get sigma over epsilon, and you get elastic. Right here, you don't need any confinement. It's a bound material. You have to put sensors in each direction, 3 sensors, and it gets your strain value, and that's what. Here, load applied. Right here, test for strain. Rate of loading relates to different time at different temperature to get the same response. That's the same thing. I can superimpose temperature and load of testing at the same response.
I'm putting my question.
Okay. Yeah.
Which was the traffic feed and temperature from the field using the existing dynamic modulus master curve that was built in the ME analysis tool. It uses corresponding dynamic modulus for that 15 days. So here we need speed and temperature, but previously we have discussed about the calculating Brazilian modulus from the layered elastic analytical process. Then that Brazilian modulus we are not using anywhere here. So am I missing anything?
Yeah, I think this is the resident modulus. The dynamic modulus at a given temperature and frequency for asphalt is the resident modulus. So it is the equivalent resident modulus for asphalt concrete. So the resident modulus in AASHTO 93 was very different. So you are now have to transition from AASHTO 93 to payment ME or MEPDG. So that resident modulus that I kept talking up to this point for asphalt is now become dynamic modulus for AASHTO for that. So you're not missing anything. The only difference is that the dynamic modulus at a particular frequency and temperature is the resident modulus or is the E value that will become the input parameters. I hope that answers your question. All right. Next one. High temperature with high loading frequency is the same as low temperature with low frequency, right? So, if you increase the temperature, and you increase the frequency, it will give the same equation as low temperature and low loading frequency. That's exactly what I explained there. Right here, this is more graphics for you. So right here, you have temperature 1, you have temperature 2, right? Temperature solution. You can move it horizontally, right? Not vertically. You cannot change. Horizontally, you can move on both sides. This is log versus loading time. That's what I just explained. And you move to the left if it is colder. If it will move to the right, if it is that way. So you can move to the right and you get one reference temperature. You can do multiple temperatures and now you can get, and then you can shift. The shift at reference temperature is 0. The shift at other temperatures are left or right. That's your shift factor. That's a lot of other math there. So master curve. Okay, so got it. Okay, good. Different frequency is traffic speed. I just explained that, right? Range of temperature is various times. That's exactly what I said. Remember, I picked up today is different temperature. If you go in January, it'll be a different temperature, and then automatically takes from the weather data. So you're gonna have to understand where the pieces are coming in, right? If you start to blindly use the software to spit out some number, and you will not appreciate it, right? Right here, this is a very good graph here. Right here, this is actual data, 10 Fahrenheit, 40, 70, 100, 130. So as I make it warmer, my dynamic modulus drops because asphalt flows. If frequency goes up, if I load it faster, my modulus goes up. So from 0.0, I think 0.1 first, I think that's what I said before, 10 seconds to same amount is right here. And then you shift horizontally and vertically, converted frequency time, and you get this equation. That's the equation right there. Log E is equal to this is what goes into the MEPDG model. That's your reduced frequency, E star. PR is a function of frequency and temperature. Reduced time. 10 Fahrenheit, 40 Fahrenheit, 70 Fahrenheit, 100 Fahrenheit, 130. So very well explained here. This is cold temperature data, 40 Fahrenheit, 70, 100. So you can see it by heat. Testing at 130 Fahrenheit, I'm getting data at almost 10,000 seconds. And 10 Fahrenheit, I'm getting almost 10 raised to minus 7 seconds. Right? Beauty of testing different temperatures, I'm getting the same information. Any questions for me so far? All right, now we are going to cracking, completely thermal cracking, right? From there, going to thermal cracking, right here. Quick compliance at 100 seconds. This was done at Penn State. This was part of my thesis in Penn State. When I joined Penn State, Superpay was almost completed, and one of my tasks was to develop this test procedure. So this was to develop thermal cracking. So right here, this is done at -4, 14, and 32 Fahrenheit. 32 Fahrenheit is how many Celsius? 0 Celsius, right? So -20, -10 is 0. So -20 Celsius, -10 Celsius, 0 Celsius. Okay, I'm going to explain this test procedure before I move ahead. I'm going to just remind you how thermal cracking is caused. We did this last time. I'm going to do a quick review. It happens when you have a cold front, right? I'm just going to do a quick recap. This is very important so I can explain this better. So here you have a cold front, right? And you have tensile strain going up, right? As temperature drops, right? All right. Now you have E goes up as delta temperature as temperature drops. Right? So the combination of the two, I told you before, is the stress, right? Temperature drops, and then you have this, and then you have strength, right? And that's your critical cracking temperature. I want to give you before I go into the test procedure, I want to explain to you what this is measuring. This is measuring this increase in temperature. Remember, I told you, you want this to be as low as possible. How do I do it? By making this as flat as possible, you remember, or bringing it as low as possible. This curve is exactly what this is. So far. So now that I gave you a context, you'll appreciate it a little better, what we are measuring. Let's look at this. What you do is, you take a load, you apply it for a certain time, right? It's very cold temperature, right? We already discussed this, minus 20 Celsius, minus 10 Celsius, and 0 Celsius, correct? And then you measure strain, right? Again, very indirect tensile strain, and it's going to go something like that. Because over time, this is time equal to 0. I forget how many seconds, 100 seconds, right there. Fair enough? Right? It creeps, you have this, and you have something called compliance. D is 1 over E, which is epsilon over sigma, because sigma is constant. Sigma is constant, and epsilon is changing. So my compliance will increase with time, and now you do the same thing from 0 seconds to 100 seconds. Compliance D over T, which is 1 over ET, if you don't know what is exactly inverse, and I will do at this, inverse of stiffness. Okay, so this is 0 Celsius, minus 10 Celsius, minus 20 Celsius. So it is softest at 0, least soft at minus 20. Now you can do the same thing, time temperature superposition, all of that is exactly the same. That's what the 3 data set. So I can now calculate this master curve with time, which I can translate to temperature, which I just explained to you. Time and temperature is interchangeable. So if I get the time, I can easily change it to temperature, and this is what I'm trying to do. Right here, you got that, and then you also get the strength. That's where it breaks, and the strength at minus 10 is 444 psi. Get your compliance, get your data, and that's how you get your platinum. Sensitivity to benefit, this is a fun one. Let me just go through this a bit. Right here. All right, let's look at the sensitivity of results. This is a fun one to do. 20 years of flexible payment design. Okay. Climate in Albany. Level 1 input from LTPP data. Way in motion. ADTT 3000 trucks per day. So this is a fun one to do. AC surface layer 2 inches. AC base layer 4 inch. Subgrade base A1A. Subgrade A4. Got it? Everybody, simple payment structure. All level 3 inputs used. No dynamic complex measured, right? IR, this is good one. 63 inch per limit miles is the initial IR. This is same as 1 millimeter per kilometer. This means a perfectly smooth roadway. Remember, yesterday I did 1 millimeter per kilometer. This is 63 inches per mile. Failure 172 inches per mile. Everybody with me so far? As I want to take the time to explain this. AC surface cracking 1000 feet per 500 feet. 25% bottom of cracking. Thermal cracking 1000 feet. AC rutting 0.25. Total rusting 3/4 inch. These are the requirements of the payment end. Okay, 90% reliability. Remember, I told you if you increase the reliability, it will over predict the distress. Okay. AC reference temperature 70, binder volume 11, 148, so on and so forth, and that's your gradation and Poisson ratio. These are from the lab data. Superpay binder grade 64 minus 28. Baseline mix design is here. Two binder contents, 70 minus 28, 58 minus. Does anybody know what 70 minus 28 means? Anybody? You got it.
70 temperature between phase.
Yes.
And 28 in minus negative temperature.
It will crack. Right. So the binder is good enough that at 70 Celsius, as long as the temperature stays within 70 Celsius, it will not rot. If it says above minus 20, it will not crack. 58 in minus 20. Good? You're good? Which one is softer? B is softer or C is softer? B is softer or C is softer? C. B. C.
C.
Yeah, B cannot be softer. It does not rot at 70 Celsius. How can it be softer? Right? So C is softer, correct? Because it does not rot at 58 Celsius. So if you go 82, 86, 88, it goes in. Yeah. Air voids. 4% versus 12%. Simple sensitivity analysis. Binder volume 8% by 4%. Remember, we started with the baseline. Certain baseline. Gradation is given to you. First one. This is the fun one. This is only surface fatigue cracking. Look at this. This was done at the baseline. 12% voids, 4% voids. As we increase the air voids, it reaches the limit right here in 24 months. So my increasing the voids by 3 times, this is 7%. Right? At 7%, it reaches in 120 months, give or take 10 years. Got it? And you can clearly see this, right? You're seeing this rutting happening. Can you see that? Right? You are seeing the rutting, fatigue cracking. So you are seeing the fatigue cracking happening. So this is the sensitivity of longitudinal cracking happening there. Let's look at the effect of gradation and binder content. Right here, let's look at one thing at a time. Baseline is right here. If I increase my binder content, asphalt is more flexible, can handle cracking better, right? Remember, flexible is good, so it has more binder. My cracking has delayed from 120 months to 192 months. I got another 6 years, 72 months, correct? By increasing by 8 to 14%. If I drop my binder content to 8%, from 11 to 8%, sorry, from 11 to 14, I am now dropping at 6. Very important thing. Many people rush to assume that this is the truth. This is not the truth. There's only one truth, the feed performance, right? So people plug these values, not realizing that there's so many assumptions. This is just one tool. Until you calibrate and validate the model, this is just number crunching, because everybody else. It's a great tool, but many people use this as the truth and do all the analysis based on this being the truth. Very risky. It's an academic exercise, but very risky. Does that make sense? Next one. Effect of air voids. Right on alligator cracking, very minimal. 0, 4, 12, because it's a bottom-up cracking. It's from tensile strain to the bottom. Effect of air voids on rutting. You have baseline 4 and 6% and 12%, 4, 6 and 12%, and you can see quarter-inch rutting right there. And you can see a big impact. Let's look at this a little bit. Baseline is 7%. If I've gone from 7 to 12, I get a few months, not too much. Not a big difference, right? I'm looking at the design limit of quadrants. So I'm getting some impact, but not that much. But questions for me? Any questions online? Thermal cracking did not appear sensitive to any changes in mixtures because it was at very cold temperatures. Right here, smoothness, IRI. That's your smoothness and design limit. I don't know why it is 200. I thought it was 170. It might have moved from the figure. 172 was the requirement. Binder volume is sensitive. Air wide content is sensitive. Other parameters appear less sensitive. Local calibration. That was the question that came. You have to locally calibrate. And then every state has to calibrate of their own. And we did that for fatigue cracking in 2008 for New Jersey DOT. You have to do in-situ stress. They did that project in Pennsylvania. They are doing all of them. This is a very old slide. This project is finished. We did level of inputs, asphalt lab testing, design guide analysis, and sensitivity analysis. Questions for me? Any questions online for me? No, none so far. Anything else you want me to cover in terms of the slides and supplements? I'm trying to look at any other material plans and introduction. We have all of them covered to some extent. Okay. I had something on payment maintenance. I can go through that really quick. And that will be the here 1230, right? All right, I'm just going to go through this payment management and rehabilitation. I have these slides, and so I'll go through that. I've done a workshop for New Jersey DOT, and actually I'm going to do one more in October for them. So just looking at deterioration, payment management, and rehabilitation, a little shift from payment ME design. Describe the need for payment monitoring, payment maintenance, and rehabilitation, and concept of it. So US is completely moving to payment preservation to come at the right time, preserve the payment, right? Monitoring, maintenance, right? Resurfacing is very, very expensive, right? So you want to come back within less than 0.75 and repair the payment. For rehab, resurfacing, restoration, rehabilitation, and reconstruction. You want to avoid reconstruction as much as possible. It's very expensive. So to be eligible for funding, the payment project shall provide performance period for at least 8 years. The requirements to determine the current state of the payment determine roughness, length, and percentage of category. RUD cell. I apologize for that. RUD cell. Joint deterioration, crack, and joint open. Right here, you're looking at easels per million, deterioration of joints per mile goes up, cracking goes up, faulting increases, PSR or PSI goes down, right? You have pumping keeps increasing or run depth keeps increasing with the design done. Payment rehabilitation selection process has to be developed by the state DOT. You have to determine the evaluate in-place payment with respect to traffic loading, environmental conditions, and material problems, right? You have to develop a feasible alternative to account for deterioration, repair existing distresses, and then to prevent occurrence of distress. You have to do project level analysis and network level analysis. You have to conduct analysis for expected performance, and then you have to do economic analysis for service life, initial cost, maintenance cost, and future rehabilitation. And then you have to find alternatives. You have to design with consideration of the most recent distress. You have to include structural capacity, foundation support, and surface drainage characteristics. And you have to document all the data, construction data, and good performance and market. Most of the pavement construction are rehabilitation of existing pavements. Full depth construction is expensive and unnecessary. So if you do not come in at regular intervals, you will have an issue. You have to do remedial action and come back and get that PSI up to 5 as soon as possible. This is the one. I like to show this graph right here. From 4.2 to 2.6, there's the drop, right? And as you keep going down, this is an overlay, right? The longer the line, the more expensive, right? So if I go from 4.2 to 2.0 and I try to come back up, it's exponentially more expensive, right? And that's what we want. This also is too much. You should come back at around 4 and do a quick repair. If you can, if you have it up, then just keep it up. Because remember, you don't want to be in this curve at all. If you can prevent that, you will keep the state. So I just want to add a couple of things. New Jersey DOT tells the federal government that I will keep the roadway, the entire network of New Jersey DOT in the repair, in the condition of good, 80% of repair at the state of good condition. Okay? They promised the federal government that number. If they fail that number by certain number, right, depending on how much they fail by, their dollars are reduced. If they exceed, they can ask for more money from the federal government. But there is a process to that, right? So there are two problems, right? DOT could cheat and reduce the bar. Say instead of 80%, I'm only going to promise 70%. But why give a very high bar, fail it and not get the money, right? But DOT's notice, US DOT, oh, you are dropping the bar. You cannot drop the bar. You know what? I will make failure instead of 40, I'll make it 30, 20. You cannot do that, right? Does that make sense? So this is very critical, and it incentivizes DOTs to make sure to come in and repair all of that to keep under good condition. Does that make sense to you? Because otherwise, they will go below that 80%. That means only 20% of the roadways should be fair or poor. Does that make sense to you? So tremendous amount of pressure to maintain that. Does that make sense? That's why New Jersey DOT has introduced 15 cents for every 4 liters of tax for traveling people. So they have close to $1 billion every year to keep the condition in good condition. So the traveling public demands it. Does that make sense? What is the problem happening now in the future? Electric vehicles are coming. They are not using gas. Batteries are heavier, right? So the cars are heavier. They're using the roadways, but they're not buying gas. They're not buying petrol, right? So what they did, they increased the registration fee. They increased the registration fee, $100, $150 for the first 5 years. So they are doing all kinds of things because they said, you are using the road, somebody has to pay. So these are the things that's very important. Construction of a new structure layer over the road layer, you need to know the existing condition of the roadway, you have to do applicability testing as well. Passing cost, it goes up, percentage area path, right? And so the packing cost goes up, overlay cost is also has to be checked. So you have to look at keep the total cost down.
Sir,
Yeah.
but like in India, you have toll tax and toll booths, sir. The same as in the US.
Yeah, they have toll tax, absolutely. So there are certain roadways that is completely. I'm glad you brought this up. There are certain roadways that is not at all funded by the government. It's completely funded by toll roads. Okay, and the toll is very high, but it's like a fast way, very good. What has happened in these toll roads, fortunately or unfortunately, they have so much money. They have actually surplus money because people pay, right? All they care about is making sure that the ride is smooth. Because people will complain, oh, I'm paying the toll, I want the smooth ride. They don't want any traffic jam due to construction. They come in the middle of the night, they construct and they leave. What is happening is that all these people don't want to innovate. Like, why innovate? Like, that is not my interest, right? So when I meet them, like, no, for me, this particular mix is working fine. It is expensive, let it be expensive. I have the money. They have no incentive to innovate. So sometimes it is hurting the industry as a whole, but in their business model, their job is to serve the traveling public who's paying the toll. So I have seen the flip side, like they will not use any recycled material. Absolutely not. Because too much urgency, what if it fails soon? What if they see construction crew come in 2 years instead of 5 years, right? So no recycled material. So it has worked against that. So I'm glad you bothered about it, and this thought came in my mind. Pothole repair of asphalt, concrete, fatigue cracking, crack sealing, surface treatment. Full depth repairs. Distress near transverse joint, decracking, we looked at that. Spalling and faulting of intermediate transverse crack. These are the techniques. You have to install double bars, corrosion resistance to epoxy fillers, stainless steel coating. Partial depth repair, you must remove shallow areas of treated concrete. They should have the same strength and stability. You have to slab stabilization. There's a whole industry, and I'm just giving a small flavor. Right? Joint and crack sealing is what you have to do. You have to do for transverse joints, longitudinal lanes, all cracks on pavements. And these are these little things that keep it at 5 level. Explain the fundamentals of payment duration, monitoring, and payment maintenance. That's all I have. I think we are ahead of time, but I'll take questions.